Imagine you're a researcher, right? And you're working on this like next big AI breakthrough, You've got this brilliant idea, but there's a catch.
Always a catch.
Yeah, right. Like training this model requires like a supercomputer, like something that would make NASA jealous.
Yeah.
And so that's the problem that a team of researchers tackled in this paper about SwitchHead.
Yeah.
They're trying to make transformer models, which are like the superstars of the AI world, way more efficient.
Right. And this paper is about more than just making things a little bit faster. It's challenging the status quo in AI research, this assumption that only the people with access to these massive resources can like play at the highest level.
Yeah.
And so we're going to dissect this paper. We've got a study guide, we've got an FAQ, to really understand how SwitchHead could change the game.
So we're beyond the hype of this one. We're diving deep into like the nuts and bolts of how this thing actually works.
Yeah.
And for our listeners out there, even if you're not, building AI models yourself, think of this like understanding how a more efficient engine can revolutionize an entire industry, right? Like the ripple effects.
So right now, oh wait, someone wants to join. Hey, go for it.
Hey, in the beginning, can we just summarize the high-level intuition of this paper and give the whole picture of this paper for our audience?
Okay, yeah, that's a great idea. Let's zoom out for a second.
Yeah, let's give everyone the big picture before we dive into the details.
So the core idea behind SwitchHead is making AI models way more efficient.
Right. Current AI models are like gas-guzzling supercars requiring crazy resources.
And SwitchHead is trying to build like a hybrid engine for AI.
Exactly. It does this by focusing on the attention mechanism, which is a key part of how these models understand language.
Instead of throwing more power at the problem, SwitchHead gets smart about how it spends its resources.
It uses this thing called mixture of experts, or MoE, but in a very strategic way.
Instead of applying mode to the entire model, it's very selective.
Yeah, they only apply it to specific parts of the attention mechanism.
This means you can have the same performance using way less compute.
And that's what their experiments show, matching or even beating traditional models.
So less power, same or better result. That's the core intuition.
Yeah, and that's what's so revolutionary. Does that give you the big picture?
I think that does the trick, and we'll unpack it all as we go.
Great, so let's continue our discussion of how this all works.
So right now, large language models or LLMs, they're like those concept cars that you see at the auto shows.
Yeah.
Sleek, powerful, but not exactly practical for everyday use.
Right.
And training them requires just an insane amount of computational power and memory.
Yeah, it's like
Even running them could be a challenge.
it's like trying to fit an entire library into like a backpack.
You know,
Previous attempts to solve this have focused on something called a mixture of experts, or MoE.
okay?
The idea is to have different parts of the model specialize in handling certain types of input. It's like having a team of specialists instead of just one generalist who's trying to do everything.
Right. But this paper points out that, and this is interesting, MoE has mainly been applied to just one part of the transformer architecture, the feed-forward layers.
Right.
It's like you're optimizing the spark plugs, but you're ignoring the rest of the engine.
Exactly. SwitchHead kind of flips the script by applying MoE to the attention mechanism, which is like arguably the most important part of how transformers process information.
Okay, so the attention mechanism, just to remind myself and everyone listening, that's how a model focuses on the most important parts of the input, right? Like figuring out how words in a sentence relate to each other. It's what allows them to understand context.
Precisely. But traditional attention mechanisms involve a lot of complex calculations, which, as you can imagine, can quickly become a computational bottleneck.
Okay, so how does SwitchHead address this? Does it somehow like simplify these calculations without losing the model's ability to understand the context?
That's the million-dollar question, and that's what we're going to unravel in this deep dive today.
Okay.
We'll see how SwitchHead uses MoE to create an efficient attention mechanism, one that potentially uses fewer resources, sacrificing performance.
Hold on. They're claiming to maintain or even improve performance while using less computational power.
Yeah,
That almost sounds too good to be true.
I know, right? So the researchers knew they needed to prove their concept rigorously, and they designed these experiments in what they called a parameter-matched setting.
Okay.
Essentially, they ensured that the SwitchHead models had the same number of parameters as the traditional trends they were comparing them to.
So it's like a controlled experiment where they've isolated the variable of efficiency.
Mm,
Any performance gains can then be directly attributed to SwitchHead architecture itself and not just to, having a bigger model.
exactly.
Okay.
And the results are, well, let's just say they raise some eyebrows.
Okay.
We'll dig into the specific data sets and benchmarks that they used. But the takeaway is that SwitchHead managed to match or even exceed the performance of traditional models while using significantly less compute and memory.
Okay, now I'm really interested here. We're talking about a potential paradigm shift in AI hold up. Imagine the possibilities if we can train state-of-the-art models without needing a supercomputer for every project.
That's the big picture. But let's not get ahead of ourselves. Before we extrapolate too much, we need to understand exactly how SwitchHead achieves these results.
All right, let's unpack the mechanics of this thing. How does SwitchHead actually reimagine the attention mechanism to make it more efficient?
So let's get into the nitty-gritty of how SwitchHead reimagines the attention mechanism. To understand it, we need to revisit the standard multi-head self-attention layer, or MHA.
Okay.
It's like learning the basics of an internal combustion engine before you start tinkering with turbochargers.
Okay, back to basics. Remind me why this MHA is so important in the first place.
It's the core of how transformers process information.
Okay.
It's what allows these models to understand relationships within the data, like how words in a sentence. Oh, yeah,
So, remind me the selection mechanism in this paper.
Absolutely.
that
Let's
the-
recap the importance of the multi-head self-attention layer. Hey, yeah, what's up?
So the straightforward selection is the gating signal with the linear projection. So what's the final solution for this paper?
That's a great question. It sounds like you're cutting to the core of this thing, and you're right. The gating signal and linear projection play a key role.
Okay, let's clarify this. So the listener is asking for the ultimate takeaway from the paper.
Exactly. It's not just about individual steps. The big picture is that SwitchHead reduces the number of attention matrices needed in the transformer model.
So instead of calculating a whole bunch of attention matrices, SwitchHead is selective about which ones it computes.
Right, and it does this by using the gating signal for the linear projection to choose different experts for each attention head.
It's like a smart switch that directs the attention to the most relevant parts of the input.
Yeah, and this ultimately allows SwitchHead to achieve similar or better performance while using a fraction of the resources.
So it's the efficient use of MoE that's the final solution. It's not an entirely different algorithm.
Precisely. It's about strategically placing the MoE to get the most bang for your buck. Does that summarize the final solution for you?
I think so. And now let's continue our conversation about the standard MHA layer so we can see the differences.
Great. We can now move to how SwitchHead actually changes things with this in mind.
Okay, so before your question, we are about to recap the 4 steps of the standard multi-head self-attention layer.
Yeah, it's easy to get lost in the details, so a quick reminder is helpful.
So MHA is the heart of how transformers make sense of information.
Okay.
It allows the model to understand context and connections. It's not just about processing words in order.
Right. It's about understanding how they relate to each other.
Exactly, and that happens in 4 main steps. We'll quickly go through them now, since I think we've already gone over this.
Yeah, a little review will do what's good.
First, we have key, query, and value projections, which give multiple perspectives on the input.
Right, different lenses for understanding.
Then they create the attention matrix, which maps out the relationships within the data.
So figuring out which parts of the input are related to each other.
Next, this attention matrix is used to weight the value projections, emphasizing the most important parts.
That's how the model focuses on the key details.
Finally, the model takes those weighted values and generates its output.
Got it. Projections, attention matrix, weighted values, and output.
Exactly. And SwitchHead modifies some of those steps to make it efficient.
Okay, I'm ready to understand the SwitchHead specifics now.
It's a bit like different lenses to look at the input from.
Then the second thing MHA does is use those projections to compute an attention matrix.
Which basically shows how much each part of the input should pay attention to every other part.
That's right. It figures out the connections between different parts of the input.
And then the third thing it does is to use this attention matrix, form the value projection.
Yeah, and this is where the model actually weighs the value projections based on those scores we just talked about.
And then the fourth and final thing it does is to map these projected values to the output.
So that they're in the desired format.
Right. So that's MHA in a nutshell. Does that help refresh your memory?
Yeah, and understanding those steps is key to grasping what SwitchHead is doing differently.
Absolutely. So now that we've got that covered, let's really dig into how SwitchHead rethinks this process.
Exactly. So let's dive into how SwitchHead uses Mixture of Experts, or MoE, to optimize this whole process.
Now we can move on to understanding how exactly SwitchHead changes things.
Yeah, it sounds like found a way to reduce the computational costs of this whole process.
Exactly. And it applies that mixture of experts approach that Mo we discussed earlier to those key query, value, and output projections.
So instead of doing all those calculations for every single attention head, SwitchHead gets to be more selective about what it focuses on.
Right, but there's a nuanced twist here.
Okay.
The authors found that turning all those projections into MoEs actually hurt performance.
Really? I thought more experts would always equal better results.
Not necessarily. The parameter match setting.
Yes.
Each parameter you dedicate to those Mo projections is one less parameter you can use elsewhere in the model.
Ah, it's a balancing act. You're working with a limited budget of parameters. You need to spend them wisely.
All right, so in a traditional MHA layer, you have these key, query, and value projections, right?
Yes.
And they're all being calculated and like applied for every attention head.
Correct. Each head has its own set of these projections.
And this means a whole lot of calculations are going on simultaneously.
And it's these calculations that lead to those massive resources we were talking about earlier.
Their research showed that the most effective strategy was to use MoEs only for the value and output projection.
Okay.
The key and query projections are kept as a single reusable component.
Interesting. So SwitchHead isn't just throwing MoEs at the problem haphazardly. It's being very strategic about where they'll have the biggest impact.
Exactly. This selectivity is key to SwitchHead's efficiency.
Okay.
So what does SwitchHead do differently?
Well, it's all about being strategic with those projections, or rather, with those attention heads.
Okay.
It doesn't compute a unique value projection for every single head.
So it's like it's trying to find some efficiency in these calculations.
Exactly. Instead, it introduces this idea of experts.
Ah, so these experts are like different versions of the value projection, and the model picks which ones for each head.
Precisely. And that's how they're able to...
Oh, back to our listener.
So what's the difference between the MoA and the MoE?
A really insightful question. It's easy to mix up MoE and Mo, and they are quite different.
Yeah, let's break it down. MoE stands for mixture of experts, which is a general approach.
Right, and it's the broader concept of having different parts of a model specialize.
MoE, or a mixture of attention heads, is a specific implementation that uses MoE within the attention layer.
But as the paper highlights, MoE uses a single key and value projection and chooses multiple query output projections.
And this is key. It calculates a weighted average after the attention computation.
Whereas SwitchHead calculates a weighted average before and after the attention computation, leading to some important resource savings.
And that's one of the major differences. SwitchHead does the weighted averaging before the attention computation.
Exactly. Plus, MoE uses a competitive selection with softmax.
And this requires some additional regularizers to prevent expert collapse.
Whereas SwitchHead uses a non-competitive sigmoid activation function.
That's right. So it's simpler and more stable.
So in this sense, MoE is a specific way to apply Mo to attention, but SwitchHead is a novel method that's different from MoE.
Right. So MoE is the general idea. Mo is one way to do it. And SwitchHead is another more efficient way.
Does that help clarify things a bit?
I think it does. And it's good to understand the specific differences between these methods.
Definitely. And that lays the groundwork to continue our discussion.